Okay, then with your consent, I have started to record the lecture. Yes. Just a second, I'm just setting up things. Okay. Is my screen visible? Someone asked. Okay. So, uh, Raghu sir has mentioned that some of you are working in to apply neural networks. Neural networks. Networks to PDs. Right. So, I think most of you are using, when it comes to PD and you want to numerically simulate things, so it can happen in two ways. I mean, there are many ways. You basically have in order to numerically perform some machine learning algorithms or neural network or algorithms, you need to approximate your PD by a finite difference method or something called finite element. So, how do you know that your approximation is good? Approx is good, and so on. So, I'll be basically discussing some concepts regarding to PDs too. So, it's kind of a bonus to all those who are working in PDs, saying that this is an interesting math stuff. Okay. So, firstly, I'll talk about something called theory of distributions. Why is my pen not working well? Hello. Okay. So now I'll speak about theory of distributions. Theory of distributions. So this is basically something called starting. Okay, so you can divide PDs in two parts. So there has been PD study, study on partial differential equations. Okay. Okay. Hi there, Bashish. Okay. So there has been theory of PD. So I'll be basically talking about something relating to modern theory of PD, which basically helps us generalize concepts of PDs, and moreover, when you apply your finite element analysis, uh, finite element methods, which most of you are civil engineers here, so finite element methods and so on and so on, you'll find these methods to be helpful. I mean, basically, to show that your approximations are good enough, I mean, to apply your optimization or neural network algorithms, you need to have this robust math behind it. So now, what is a distribution? So to understand what a distribution is, it's not a story of one class. So right now I'll give an abstract definition of it, but as we progress on and get some kind of a mathematical intuition as the lectures progress, you will understand what a distribution is. So basically, a distribution is generalization of a notion called notion of functions. Okay, for now the kind of definition is overwhelming. So we basically have function. Function is a map from some kind of, basically a function is a map from some kind of vector space to Rn. It need not be a vector space. It may be a vector. It can be a metric space or a set. So function is basically a map from a set to real line. So if you add some properties on this set, you make it a vector space, and then you add some kind of notion of distance. It becomes a metric space, and then you add a notion of completeness. It becomes a Banach space, and then you add a notion of orthogonality. Then it becomes a Hilbert space. Again, if this space has some sort of differentiability properties and so on, you will go to Sobolev space. Saying that, please don't worry if you don't know any of this. If you know, it's good for an intuition. But right now, just understand that, I mean, as we progress in our class, I'll be explaining each and every term that I speak of. So for now, your function basically takes in a mathematical element and gives out a real number. That's it. An example, sin x. So sin x basically takes a real number and gives out a real number. But now say I'm taking f of x1 comma x2, and which is equals to x1 square plus x2 square. So basically your function is defined on a vector space. It basically eats up a vector and gives out a real number. So that's a function. So now we are basically trying to classify these functions. So, I mean, yeah. And why are we doing that? Okay. Why are we generalizing the concepts of function? So there is a stark difference between your ODEs. ODE in the sense ordinary differential equation. Ordinary differential equation. And a PDE is a partial differential equation. Now say hypothetically you have an ODE x dot of t is equals to a times x of t, where thank you, I have forgotten to share the screen and all of you are seeing from the entire time. Thank you. Okay, thanks. All of you have been seeing an empty screen so far. Good. Okay. Okay, so I was basically explaining that we have an ODE, ordinary differential equation, and a PD, a partial differential equation. So let us say you have an ODE x dot of t is equals to ax of t and x of 0 is equals to x naught. So say you solve this ODE. So you have the solution x of t is equals to x naught into e power at. A is a scalar obviously. Okay, so this is one solution. Say you integrate this both sides. So x of t is equals to x naught plus integral 0 to t x of sigma d sigma into a. You solve this expression recursively, you get x of t is equals to x naught e power at. So this is second solution. These both solutions are the same. Okay, and then you basically multiply this ODE with some scalar, say b times x dot of t is equals to ba into x of t, and you solve this ODE. Again you get x of t is equals to x naught e power at for all b in R. So okay, but in PD you won't get like this. So the differential equation and the integral equation in the case of ODEs give you the same set of solutions, but in the case of PDs you won't find the same. So you might be asking, okay, fine, but why can't I solve the PD directly? Why is that I have to integrate by something and then we'll get things? So here, okay. Okay, so as I told, some of you are using finite element methods. So in PD, the same set of equation will give you three different solutions. I'll show you how. Consider consider Burger's equation. ut plus uu plus ux is equals to 0, and so I've compared ODs to PD. Just a second. You have an OD, you have a PD. Say you have some x dot of t is equals to ax, implies x of t is equals to x0 into e power at. This is one of your solutions. Say you have a Burger's equation ut plus ux equals 0, where u of x comma 0 is equals to h of x. So I hope every one of you might have studied how to solve PDEs, method of characteristic equations. You are usually taught in your BTech first year, but then we forget things, so we have to revise things again. So I'm revising again. So you have you basically have you solve this PD this way. So dt by 1 is equals to dx by u, which is equals to du by 0, implies dt by ds equals 1, dt by dx by ds is equals to u, and du by ds is equals to 0, implies u of s is equals to u is equals to h of s, x is equals to s h of s. Yeah, sorry for the disturbance. Okay. So I'm solving the PD. Sorry for the disturbance. I guess people from my hostel are absolute useless. Sorry. Yeah. So they basically disturb us. Yeah. क्या करेंगे Satan. Okay, so you have a PD ut plus ux is equals to 0, and u of x comma 0 is equals to h of x. So this is our PD with the initial condition. So the method to solve is this. So you take some dt by ds. It's a shortcut method. There's a big story behind on how to solve this PD characteristically, but as we are engineers and we like shortcuts, so dt by ds equals the coefficient of u of t 1, and dx by ds is equals to z, and so we take the initial conditions, x is equals to s, t is equals to 0, z is equals to u is equals to h of s, and dz by ds is equals to 0. implies z is equals to h of s, x is equals to initial condition of x, s plus zs, and initial condition of t is equals to s, implies so z is equals to h of t plus st, implies u is equals to h of t plus st. So you have a solution that need not be differentiable, but that solves this. Okay. So I have shown that you can basically directly solve the PD like this. For example, Burger's equation ut plus ux equals 0 has an implicit solution h u plus xu or something like this. And one more method which I have discussed regarding ODEs, x dot of t is equals to ax, implies integrating on both sides. X of t is equals to x of 0 plus a integral x. So if you solve this particular integral equation by successive approximations, you get the same thing. But this is not the same with the PD. You integrate this with respect to time. U plus integral 0 to t ux is equals to 0. If upon solving this particular integral equation, you won't get the same thing. So in an ODE, you integrate the ODE and find a solution of the integral equation. You get a solution which is same as solving the differential equation. But in the case of PDs, you integrate the equation and solve the integral equation. You won't get the same thing. Similarly, and now if you just multiply your x of t with some kind of a weight, x dot is equals to b is equals to axb, where b is a scalar, and again you solve that, you again get an ODE. But in the case of PD, you multiply it with some weight function phi dx plus integral ux dx d sigma equal to 0. You won't get the same. And this is something that you use in your finite element methods, if anyone is familiar. Okay, so far if you don't understand things, it's okay, you can contact me. I'll repeat them, I'll elaborate everything in the consequent classes. So what I'm saying is that an ODE will have a unique happy solution. You integrate and solve it, it will give the same equation. You multiply it with a constant and solve it, you will get the same thing. But a PD will not have a happy solution, will not have a unique solution. You solve the PD directly, you get a different solution. You integrate the PD and solve the PD, you get another solution. And you multiply it with some weight function on both sides and solve the PD. This is also called Galerich and FEM, finite element methods, which most of the civil engineers use. You will get a different equation. So now, in order to generalize all these things, we have something called a distribution. Okay. So now, again, mathematicians, we have definitions. So L2 of R is equals to all such functions such that integral R mod f square d mu is less than plus infinity, and you can basically identify your L2 of R with its dual. So don't get too afraid of this thing. So basically your L2R is basically connection of all square integrable function. So you take a function, and if the integral, if you square it, and if the integral is finite, then the function, and you collect all those functions and you put it in a basket, that basket is called L2 of R. L stands for Lebesgue. Lebesgue is a mathematician who basically gave this kind of, basically Lebesgue is the one who generalized the notion of integration. So we name this set of functions to honor him as Lebesgue integrable functions. Okay. So now to know a function, to know f belonging to L2 of R, you identify with its dual. Phi g is a functional in the dual space L2 of R star, such that implies phi g of f is equals to integral of R into f g d mu. This is by Rees lemma. So I'll just vaguely write a statement. See, in mathematics things are non-linear. You have a definition and then you proceed. You don't understand the definition, yet you proceed, and as you proceed, you get to know the definition. It's something that we have to go through, but then all the physicists that we respect today are actually known for these abstract things. So to know g in L2, it is sufficient to know this particular integral f g dx for all f belongings to L2 or all f dense in L2. That means what's a dense set? So basically, say you have something, say I give you some squares, set of squares. So I can use a set of squares to basically fill these circles. So I can basically consider any amount of rectangles and try to approximate this set of, we can approximate this circle. So similarly, say you have L2. L2 is basically all functions such that function is square integrable. So you just imagine this to be a circle for a while. This to be rectangles. So these set of rectangles should be good enough to approximate any G in L2. Okay. So now previously I have given something called definition of function. Basically function is something that eats up an element from a set and gives a real number. So now let phi be a function from Rn to R. So basically what does it mean? Rn is basically some elements like x1, x2, so on till xn. Each xn belongs to R. So, and if now I define support of f, support of phi is equals to all x in Rn such that phi of x is not equals to 0 and support of phi is the closure of this elements. So if support of phi is bounded, implies support of phi is compact in Heine-Borel theorem. So basically what does this mean? So let us take phi from a phi from R to R. So if a comma b is support of phi implies your function vanishes outside a comma b. Implies, say you have function. So okay, just to visualize purpose, say you have a function that's doing something and just vanishing outside like this. So this is called a function that is supported on the interval a comma b. So basically your function should vanish outside the interval, then it is said to be supported on that particular set. Okay. So now let me define something. Let omega subset of Rn be an open set and d of omega be all f such that f belongs to C infinity in omega and support of f is compact. Yeah. So this particular set is called space of test functions. Okay. So I'll give an example of a test function f of x is equals to e power minus 1 by x square and 0 x square for x greater than 0, for x less than or equals to 0. So how do you think this function will look like? So it's 0 at x equals 0, this goes to plus or minus infinity, so it's 0, and at 1 it's e power minus 1. So it attains some sort of, so let me draw this graph. Differentiate f implies e power minus 1 by x square into minus 2 by x cube is equals to 0. This is possible only at 0, and then at infinite x will become 1. Oh, okay, so this graph will be something like this. I don't think it will attain a maxima, so sorry. No, when you want to draw a straight line, the support will be converging to 1. Yeah. Let me check if I have drawn the graph right. Exponential of minus 1 by x square. Thanks. Graph. Okay. So it's right. So my claim is that this particular function is infinitely differentiable. So I'll prove. So you have the function f of x equals e power minus 1 by x square, and you differentiate this any finite amount of times, what you get is some kind of linear combination of x power minus k into e power minus 1 by x square. So now I just have to prove that limit x tends to 0 is this should be 0. See, basically it is differentiable everywhere, here and here. Only point that you have to take under consideration is 0. If it is continuous and infinitely differentiable at x equals to 0, then you are done with. Okay, let me take this g of t power k into e power minus t, which is less than or equals to k power k e power minus k, implies t of t e power minus t is less than or equals to k power k e power minus k, implies x power minus So if x less than or equals to 1 by root k, less than or equals to x power minus k, k power k times power minus k implies limit x tends to 0, x power k into e power minus x square goes to 0. So derivative is 0 at this point. Okay. Similarly, another example. So you have f of x equals a square by a square minus x square 0 less than a and mod x goes to a. This function also belongs to, it's an infinitely differentiable function on R, and also this is bounded in between minus of a. So basically f belongs to domain of I guess minus a comma a, because omega has to be an open set. This is an example to prove that this is infinitely differentiable and also is compact. It basically vanishes outside a. It's pretty straightforward, not that same as the previous example. Okay. So now we just go and advance this concept. I'll define something called modifiers. Okay. So let x is equals to x1 so on until xn. This is a vector in Rn. Implies this is basically a Euclidean distance on x. So I basically define rho of epsilon of x is equals to k epsilon times minus n e power minus epsilon square by epsilon square minus mod x square 0 for mod x less than epsilon, for mod x greater than or equals to epsilon. So again, extending the previous theorem, this is basically an infinitely differentiable function and compactly supported on minus epsilon to epsilon. So basically this is a function that vanishes outside epsilon. So you take an epsilon smaller and smaller, you get a pulse. Infinitely differentiable smooth pulse. Yeah. Go on like that. And basically you choose your k. You basically normalize this thing. So k is nothing but 1 by integral of mod x less than or equals to 1 times e power minus 1 by 1 minus mod x square dx. So just check that integral of norm x in R is rho epsilon times of x should be 1. Yeah. Okay, I guess with that, I guess we can end today's lecture. I thought of revising concepts from lecture 1 and lecture 2, but I guess we have 10 more minutes and it isn't sufficient. So, with that, we'll end today's lecture. Thanks for coming.